It's with alkenes that we can see our first reactions. And I want to just note a few things before we start into actual reactions, because I've had some confusion with this in the past, and I just want to make sure that everybody's on the same page here. It doesn't really matter if you write something A plus B, at least in organic. You know, it does when you're balancing equations, and we do things a little bit differently with organic sometimes than in other areas. But we can say this, like A plus B in the presence of Z, that's what that means, gives you this. Sometimes we'll take B and move it on top there, or beneath it. It's the same thing. We're taking this and we're turning it into that. It doesn't matter what's on top, what's on bottom, as long as you don't have a number 1, number 2. Now that's a little bit different, but we'll get to that when we get to that. So I just want to make sure that you know that all those are really saying the same exact thing. Sometimes also we don't really write all of the products of an organic reaction like you did maybe with inorganic compounds. And the reason for this is we want to make sure that you're focused on the organic stuff. And yes, absolutely, the other stuff exists, but we're just trying to focus on what's happening with the organic stuff, because that can be complicated enough by itself, for sure. Okay, so let's start by looking at hydrogenation of double bonds. What that means is we're going to take this double bond right here and add hydrogen to it. When you add hydrogen, you're actually adding a hydrogen here and here, and that's what makes that double bond go away. It's not that the double bond just disappears or anything like that. And so let me show you this to show you how and why that happens. So if we draw out all the carbons and the hydrogens, see how there's that double bond right there? By adding hydrogen, we're actually adding a hydrogen here and a hydrogen here. So that's where the H2 is going, is that they're being added right there and there. Just the same way if you reduce a bond or you take away 2 hydrogens, you have a double bond. If you add 2 hydrogens, you have a single bond. And that's what hydrogenation is. It doesn't matter if it's in a ring or not, this is the same concept. We can use platinum, we can use palladium, we can use nickel. Actually, there's probably lots of things that we can use, but that's all you really need to know for right now. So here we have a double bond, and again, by taking this to a single bond, what we're adding right here is another hydrogen, and what we're adding right here is another hydrogen. Sorry, I probably should have made that a different color, but if you want to do that, feel free. Okay, that's the first reaction. The next is we're going to add water. So if we add water to an alkene, this is known as a hydration reaction. Hydration, water, get it? You have to have acid in there. Now be aware, guys, acid comes in many different forms. It can be H+, it could be pH2 or pH1, you could have H2SO4, you could have HCl. All those things that you know as an acid still count as an acid. And it doesn't matter again if it's over here, if it's on top. It's all the same thing. Okay. When we add water, this is an easier way to look at it. It's going to split into an OH going to one carbon and a hydrogen going to the other. You can't really see that from up here, can you? But when you draw all these bonds out, it's much easier to see. This is not what's really going on. I'm not going to show you what's known as the mechanism, but this OH is going to go and bond with that carbon, and this hydrogen is going to go bond with that carbon. And see how that gets added? We just don't write this H because we don't write any of the H's when we draw it like this, right? That's why we needed to know how to do that pretty easily. Now there's this thing called Markovnikovs rule. Because I'm not showing you the mechanism or the way things happen, we don't really know what that means. But let me just simplify it and say that the OH part of the water will go to where there's the most carbons connected in that double bond. So see, this carbon's only connected to 2 carbons, and this one's connected to 3. If they're the same, you get a mixture of the two. But in this case, notice how I drew the acid at the bottom? It's the same thing. The OH is going to go to this carbon, or it's going to be attached to that carbon because it has the most connections to other carbons. So again, where this double bond is, see how this OH goes there and this hydrogen goes there? Then we end up with the OH on this carbon and the hydrogen up here. Sorry, again, I should have put that in a different color. Okay, you just did your first reactions. Make sure you practice that. Okay. You've probably heard of the term polymer. These are known as plastics. Plastics rule our world. That's even plastic. So it's really important that we know how plastics are going to fit in with everything we do. If you want to consider it this way, a monomer is like the basic building block of a plastic. Plastics are known as polymers in the chemical world. So basically, if this is a monomer, you put a whole bunch of them together and you make a polymer. Hence why it says poly, many. Now how long that is and what this monomer actually looks like, because it's not going to look like that, gives you the nature of what type of plastic are you going to have, because even this pen, that's made out of plastic, right? These are different types of plastic. You've probably heard of different types of polymers like PVC and that would just polyvinyl chloride. And there's PET, all kinds of different types of polymers. Okay. Okay. So now let's talk about benzene. Benzene is its own special case of awesome. It basically has a lot of special properties because it's so incredibly stable, and you'll find it all kinds of places that you may not expect. We can draw benzene. It's basically a cyclohexene, but it's got 3 double bonds. Right there, there, and there. And they're alternating. Double, single, double, single, double, single. Another way to write it would be to have the double bonds over here. But what we actually find is that there's not isolated double bonds here, or here, or here, or wherever that may be. In reality, they're kind of more loosely combined like that. Hence why we tend to write things like this. And that's where that crazy benzene structure can be. So for now, what we need to know is how to name this stuff. It's really quite similar to naming cyclohexenes. It's just that the name at the end is benzene. So in this case, we've got 2 substituents. We've got a chloro group and we've got a methyl group. You're going to number it and put it in order, just kind of like we did before. So this becomes 1 chloro, 3 methyl benzene. Now in this case, what do? We've got to figure out which one the number is going to be the best. Well, we didn't even look at this very much with our other cyclohexanes. Well, here we can go 1, 2, 3, 4, and then that gives these lower numbers, both of them. If instead we went 1, 2, 3, 4, that's going to stick them with higher numbers. So we actually would prefer to go 1, 2, 3, 4, like that. And then we put it in alphabetical order. So 2 bromo, 1 fluoro, 4 methyl benzene. Okay. Between these two, isopropyl starts with an I. This would be 4 because 1, 2, 3, 4. It's on the 4th carbon of that ring. So 1 isopropyl, 4 methyl benzene. There's other ways to name things, and you might see this every once in a while. If you consider this as your major substituent, these 2 carbons, anything that's coming off of these 2 carbons would be ortho position to that. This would be the middle or meta position to that, and this would be the para position. So think of a periscope. You know how a periscope is like on a submarine, it goes above water? So that's the opposite, right? Ortho sounds like next door to me, and then meta is kind of like the middle position. So we could also name this P or para. You could write out para, that'd be fine too, or just say P. Diethyl benzene. You can also have a benzene as a substituent. And usually this happens if you have something that's a little bit more complicated with lots of substituents coming off of a chain, or if the chain is larger than the benzene itself. So if we were to name this as a substituent, it sounds nothing like benzene. It's actually known as a phenyl group, and that's spelled P-H-E-N-Y-L. Why? I don't know. It is. So we're going to start numbering here. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 4-methyl 2-phenyl octane. This would be 4-phenyldecanate. Let's count carbons, make sure I'm right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Notice I had to erase one. I went crazy a little bit too much before I started naming it. Then, lastly, there's this special case. There's special cases that are named differently, and then we kind of use that instead of benzene. And we'll look at this as we go through the semester. I believe we're going to look at some more details here. When benzene is connected to an NH2, this is called aniline. And when benzene is connected to an OH, we call that phenol. Got to be careful there. It's phenol, not phenyl. Because phenyl was what we just did up here, right? I know, it's hard to keep track of, but this is phenol, okay? So now what I do is I use this as my name, and I number substituents coming off of there. So this is going to be assumed to be number 1 carbon because I'm naming it based on that, okay? So if this is number 1, no matter where it is, it's number 1, 2, 3. That's the easiest way to get to the lowest number. So this becomes 3-bromoaniline. You could also name it meta-bromoaniline. Now we've got phenol here. That would be the number 1 because that's where the OH is connected, and that's what we're naming the end of that by. 2, 3. So this is 3-methylphenol. Even when you have more substituents, this is still the phenol. This is number 1. Now I could choose to either number it 1, 2, 3, 4, or I can go 1, 2, 3, 4, 5. Those are higher numbers, so I want to go 1, 2, 3, 4. So this becomes 3,4-dimethylphenol.